Lesson 17, parallel circuits. What we're going to do today is we're going to learn how to interpret parallel circuits. Now, some of the content today is going to be a bit challenging, so you got to strap yourself in. If you don't understand something, let me know. I am willing to record like a separate session, like at 3 o'clock, or maybe record a video for you guys to give you guys some help with this stuff if you're struggling with it. But what I will point out is this really quickly. 2 years ago, I had to take this. I had to take a lesson off because I had to take my year nines to city site to experience. So I just had to leave them with these two circuit things from Khan Academy. These two videos on YouTube or on Khan Academy are really, really good for explaining how electric circuits work. So if you really are not getting it, and I've explained it to you already, and or you may be too embarrassed, like I don't want Mr. Greer to know that I can't do electric circuits, check these guys out. They do a pretty good job of pretty much the same sort of thing, and they might talk your language. One thing I've said to students before is sometimes you'll find that your teacher just might not speak your language. They might just not use the words that you would use. I know for some of you guys might be thinking to yourself, I don't understand why he uses these words, but another teacher might explain things like, oh yeah, that makes sense. So I always suggest explore other ways. So maybe these guys do a better job. Last lesson, the big double, what we did was electrical circuits. What we worked on was we talked about why order doesn't matter, and then we talked about short circuits and why electrons will tend to go for the path of least resistance. Electrons just don't like trying to climb big mountains. They would rather take shortcuts. And if you provide a shortcut in a circuit, then your electrons will take that shortcut. And if they take that shortcut and there's nowhere for them to drop their voltage, they'll just leave all their voltage. They'll just drop all their energy on the wire. You cause that wire to get really, really hot. Oh, by the way, one quick thing about one of those videos that I showed you the other day. I haven't really ever talked about this with students before, but you will sometimes see big electrical wires and you'll see birds just sitting on those electrical wires. You might think to yourself, why don't the birds fry up? Why don't the birds, get electrocuted? And the reason that the birds don't get electrocuted is if this wire is negative and this wire is positive, if the bird sits on the wire, then it's going to be negative. It's going to be completely charged negative, but it's not going to conduct charge. There's not going to be any charge going through the bird there because there's no positive charge. The bird might get a static shock, but when it lands somewhere else, but in general, there's no way for that bird to lose that electricity. The only way for that bird to spark is if there is a charge that jumps, if there's a stick or something that falls between the two wires that offers a path for it to go, then the bird might get electrocuted. Maybe if the stick falls on the bird, then that bird might get electrocuted. We spent a lot of time talking about electricity and lightning as well during this lesson, which I thought was interesting. Completely never happened before when I taught engineering maths, but I was actually really excited to get a chance to talk about lightning. We talked about this here. We said that in a parallel circuit, we've got the current, the resistance, and the voltage. You just add the resistance together, you add the voltage together, and for the current, it's all the same. There is no weird things we have to do here in a series circuit. In a parallel circuit, though, it does get a little bit more complicated. Because in a parallel circuit, you have to add 1 over RT to get the total resistance, and then the voltage is the same. Also, the voltage drop must be the same for each wire. Now we're actually, and then at the very end of the lesson, we did some examples with resistors in parallel, because they're usually a bit harder. And the last two bits we did is we looked at dropping electricity in a series circuit where the resistors are the same, and then a series circuit where the resistors are different. Today, we're going to move on to parallel circuits. Before we start parallel circuits, let's just do one more for this series circuit. And this one is a series circuit where, and this is sort of to say, hey, what happens if I start to make some of these X? What happens if I don't know what the resistance is? What happens if I don't know what the voltage of the battery is? Can I work these things out? The answer is yes. And the answer is going to give us, and again, when I talked about this, I said to you guys, there are multiple ways to solve this problem. Now, I haven't even, when I'm looking at this question, I haven't even thought about how I'm going to solve this problem. I'm just going to make my way through it. I can think of maybe two ways to solve this problem off the top of my head. One involves some complicated algebra. I'm gonna try and avoid the complicated algebra method, but you could do that if that's your jam. If you love that, sure. Let's start off by looking at the resistance. Can someone tell me what is the resistance through A? What is the resistance through A? And someone's already said that. They've said X, exactly. The resistance through A is X. Now, what is the resistance through B? Can someone else say? Someone has said the resistance through B is 4. Yeah, beautiful. Thank you, Jess, 4. So the resistance is 4. Now, as for the total resistance, we don't know what the total resistance is. Yeah, as I just remember when I was saying before, you could use an algebraic method. You could actually say the total resistance is X plus 4. That is a way that you could talk about the total resistance. But I'm going to avoid that for the moment, and I'll talk about that. But I'm going to avoid that for the moment. Let's talk about the current. So the current, so the total current. Can someone tell me what is the total current, and then what is the current through A, and what is the current through B? What is the current? 0.4. Thank you, Jason. It's 0.4. It is 0.4 amps is the total current. And because it's a series circuit, it's 0.4 through A and it's 0.4 through B. The total current is 0.4 everywhere. Now, the last one to talk about here is the voltage. Now, the voltage through this circuit, let's do voltage in the blue. The voltage through A, we don't know. The voltage through B, we don't know. It's not written. We do know the total voltage. The total voltage is going to be 4 volts because it's actually written on the battery. It's written in the question. Now, and then that's all the information we can drag easily out of this problem. Now, there are a couple of things here. There are a couple of things we could do at this point. And I'm trying to work out. And you might be able to, let me see. You might be able to see this better if I did this. It's gonna maybe cover up a little bit. It's going to be a bit messy, but I'm going to show you. The reason I should show you this is there are multiple paths we could go through. The first path is this, okay? Notice how we know we know I'm going to show you, and there's a couple of techniques that you could do if you wanted to solve this. Notice how we know the total voltage, the total current, because we know 2 of the 3, we could work out the total resistance. We could actually work out the total resistance. We also could do this because we know the total current and we know the total resistance. We could work out the voltage drop over the resistor B. So I'm going to leave you guys up with a choice here. Do you want to work out what RT is, or do you want to work out what VB is? Both of those will get you to the answer, and both of those we can work out now because we know RB and IB, or we know VT and IB. I want you guys to vote. Which one would you prefer to choose?
VB.
VB?
Yeah, VB.
VB, okay, fine, we'll do VB. We can't do VA. Julie says RT. I don't know why Julie wants to be different.
It doesn't matter to.
Let's go with VB.
Exactly, Julia.
Okay, so let's go do VB. So because we know, how do we do VB? Because we know V equals IR, we can work out VB is going to be IB times RB, and we know IB is 0.4, and we know RB is going to be 4 amps. So 0.4 times 4 is going to give us 1.6 volts. Okay, 1.6 volts. If I've got that correct. Yeah, I think that's 1.6. Now, if we know that VB is 1.6 volts, we now have a new choice. We can work out RT, or we can work out VA. Both of those are pretty easy to work out. Because Julia asked for it, we might as well do RT. RT, I'll do that over here, V equals IR. And the reason we can do that is because we know 2 of these things in this row. It's a little bit like Sudoku, if you will. We know R is going to be V divided by I. That means that if I know total voltage, which is 4 divided by 0.4, that means that 4 divided by 0.4 is, I'm pretty sure, 10. I know that I should know because I'm a maths teacher, but I'm going to actually double check because I have made mistakes like this before. It is 10. 10 ohms. So the total resistance is 10 ohms. That means this last little bit is pretty easy. Can someone tell me what is RA? Remember, RA plus RB must equal RC. What's RA going to be? 10 minus 4, thank you, which is 6. And then this is the part that I like, because just like in Sudoku, there are 2 ways to get the last answer. To get this last answer, the VA, the voltage drop through A. There are 2 ways to get it. The first way is to go I times R gives you the voltage. So if I went V equals IR, I could go 0.4 times 6, right? There is another way I could get the answer though, is to go 4 volts minus 1.6 volts will give you the answer. So the other way will be 4 volts minus 1.6 volts. That will tell me how much gets spent. Both of these answers come to 2.6. 2.4, exactly. Both of these come to 2.4. And it's kind of cool that both of these come to 2.4 volts, even though we found them out differently. And that also means is, again, my other point as well is we didn't need to do, if we had have worked out RT, we could have worked out, if we did RT first, we could have then worked out this second, we could have worked out this third, and then VB we could have worked out fourth. You know, it doesn't actually matter the order that you solve these in. But again, and there are usually more than one way to do it. We chose to do VB first. You may have instead chose, and then we could have done VA second. After we did VB, we could do VA, and then we could have done RA, and then we could have done the resistance total by just adding these two numbers up. It doesn't matter which way you do it. And believe me, every time I've taught this, I've done it a little bit of a different way. The other advantage that I want to show you here is if you set up your table like this, you can actually figure out quite easily what you can solve. If you have two known things and an unknown thing, you can work out either the voltage or by using V equals IR, or you can use a column. I'm going to move on now to the new stuff, and we're going to start talking about parallel circuits now. Oh, by the way, yes, you could use a complicated version of this to work out what the total resistance is and stuff like that. RT equals X plus 4 when we didn't know what RA was, and then you could have done, yeah, you could have done it. I'm not like, yeah, I'm not going to do it because I can't be bothered. You could do it. We're going to look at these three if we get time. Looking at my watch, we've got 15 minutes. We might be able to get through the fourth and the fifth one, maybe leaving that sixth one for tomorrow. But let's try this one. Let's look at this parallel circuit here, and we're going to give a crack at it. If you guys want to jot this down in your books and then do it with me as I go, now is when you should do that. And I'm going to drink a little bit of my coffee. If you've got any questions, shout them out now before we get started. All right, getting started. Now, we can start with, you know what, let's start with something different. Let's start with voltage first. Now, remember, in a series circuit, my opinion is current's the easiest one to do. The reason that I think current is the easiest one to do is because there is only one type of current. It's the same number all the way down. So, but when you've got a parallel circuit, the current splits. So current's no longer the easiest one. The easiest one is voltage. So let me show you how you do voltage. Firstly, can someone tell me what's the total voltage in this whole circuit? Someone's already said it. That was our good friend Bao for a change. Okay, I haven't seen that, and then Emery, but I haven't seen. So he's right. It's 6 volts. Now, who wants to take a guess? How much voltage is going to be dropped? And we'll call this one at the bottom A. We'll call this one the top B. It doesn't matter. How much voltage gets dropped through? Oh, that's going to get confusing. That's going to get confusing. I'm going to call this one A. I'm going to call this one B, because then the order matches. How many volts gets dropped over VA? Who wants to take a guess at how many volts gets dropped over VA? Or do we not know? You can write, we don't know, WDK, if we don't know. But yeah, how many? I don't know. Does anyone know? Min doesn't know. 3. Sang's given a good guess. Yep. Anyone else want to say how much? 6. The answer is 6 volts. You might be saying, whoa, how did I work that out? The reason it's 6 volts is this, right? And I've sort of talked about this already, but let's do it again just so that we know. If the current comes out of this part of the battery, actually I'll do this. If the charge comes out of this part of the battery and it goes through here, it's only got, and it just say it chooses to go up the top part. It goes through the light globe and it goes back down to the battery. It's only seen one item in its travels. So that means it has to lose all of its voltage at that one bulb. It loses all of its voltage at the one bulb. So because it has nowhere else to lose its voltage. It can't lose its voltage here, it can't lose its voltage here. This is different to our example before where we would have where we had a series circuit, because there were multiple places for it to lose its voltage. In this case, we only have one place. So that means it loses all 6 volts here. What's going to be the voltage drop through VB then? How many volts is it going to lose? 6. Exactly. Thank you, Jessica. It's going to lose all 6 volts here because ultimately that's the only place that it can lose it. So when current was easy for series circuit, voltage is easy in parallel because it loses the same voltage everywhere. Each branch will lose 6 volts. So the next easiest one is going to be resistance. Now the resistance is easy. We can read the resistance off for most of these. Now RA, that's going to be 3 ohms. Easy, done. RB, that's going to be 3 ohms. Easy, done. RT, now that is not going to be 6 ohms. If you guess 6 ohms, then you guess wrong. RT, and we have 2 choices. We can go 1 on RT equals a third plus a third. And then you can do that, but I actually wouldn't. The reason you might say, you could do this and work out what RT is. If you want to do that, sure, fine, go ahead. You will get something like 0.66. But at the moment, I just want to leave it for a second. I'm going to show you why in a little bit. Let's look at current now. So again, just a reminder, we could have figured this out. I'm choosing not to. The current. Oh, whoops. Oh my God. Now the current's a bit interesting. Now we can work out what the current is. We can work out what the current is through A. We know that 6 volts is getting dropped across it. So we can use V equals IR. V equals IR. Rearranging, I equals V divided by R. We can say, well, if I know that it's 6 volts is getting dropped over 3 ohms, that means the current is 2 amps. IB is the same process, 2 amps, because they're the same numbers. IT, the total current, well, that's 2 amps, and that's 2 amps. When they meet, what's the total current going to be? Bow guess is 4, Bow guess is right. Well, actually, maybe Bow knew. The total current is 4 amps. It's the sum of the amps. Now, I want to stop for a second because some people might be like, whoa, whoa, whoa. How did you do that? What? Did he just guess? remember, if this is 2 amps up here, remember then this is going to be 2 amps just before they meet. So when 2 amps meet, they go to make 4 amps. Now, this is why I left this red line blank at the start. At this point here, I could go I could work this out, but I'm going to prefer, I usually prefer to do this. RT equals V over I, which is going to be 6 divided by 4, which is going to be, 6 divided by 4 is going to be 1.5. Now, I'm not saying, by the way, I will point this out, I'm not saying that you can't just go, I'm not saying that you can't go do the other method. You can do this method. If you love your fractions, then by all means, go nuts. But I have a tendency to make mistakes. So I have a tendency to make mistakes. I just made a mistake there. So yeah, you can use that method instead. But if you can just use the V equals IR formula, I usually just prefer to do that. It's just usually a bit easier. So that's an example. Okay, I'm going to move on in a second, but before I do that, are there any questions, queries? What the hell did you do here? How did you do that? Problems from the audience? Let's check the time. I've got 5 minutes. Yeah, I'll give it a try. I'm going to give the last one a crack. If we run out of time, I'll stop it early. But, let me know. Do you guys have any questions on this before I move on, though? Someone say all G if we can move on. You can solve most circuits with those 3 things. With V, I, and R, you can solve pretty much everything. The only trick is you just need to know some of the tricks. Like you need to know, hey, in a parallel circuit, the voltage drop is the same. In a series circuit, the current is the same. If you know those 2 things, and if you know, hey, with a resistance, in a series circuit, you just add them together. In a parallel circuit, it's 1 on RT, then you can solve everything. So those are the tricks. You need to know what type of circuit it is, and you need to be good at using V equals IR. I'm going to start looking at this next one. If I get too late, could I get someone to call out, like either out loud and just say, "Sir, the class has ended"? I'm going to try and go through this. Maybe even if we just start this now. You know what? What I'll do is I'll do this. Give me a second. And then I'll do this. We're going to start this, but we're not going to solve the whole thing. Let's just, because we're going to run out of time, let's just do the voltage and yeah, we'll just do the voltage probably. With this circuit, it's again a parallel circuit. It looks a bit different. The reason it looks a bit different is because I've moved the top part up here. But ultimately, the main idea I want you to get though is that there is still a current divide here. Half of it goes up or half of it goes down. Now, really quickly, what I want you guys to see in this circuit though is this. These 2 resistors are different in size compared to this example when they were the same. That means that the current is going to choose differently. Can someone tell me, is more current going to go up or down? Ooh, straight away, different answer. Jess says up. Jason says down. Adina says up. Ooh. Ladies and gents, power of the sexes, the ladies have it. And Emery, who's not a woman. There is more likely for the current to go up. Bao missed the question. Okay, sorry about it. The reason that electrons are more likely to go up is because they really want to go, they would rather take the path of least resistance. And the path of least resistance is up because there is less resistance. So that's why the current is more likely to go up. So when we go through this tomorrow, we are going to explore the different currents. I've just been yelled at by Julia, and I think who that other person was, John, who's like, yo, the class has ended. Fair enough. John, who's being like, what did you even notice? Of course I did. Right, we're not going to do the voltage. We're not going to do the voltage yet. We have started this circuit. We are going to notice for this circuit, there's going to be some interesting things current, but we will explore that on Thursday's lesson, and I'll give you guys electronics 2 on Thursday to start working on. Guys, thanks for listening. You've been a great good class, and I will see you guys tomorrow.